So today we're looking at the dimension of the homogeneous components of the free Lie algebra. Let X be a set, alpha be an element of our naturals indexed by X, and D a positive integer. We write that D divides alpha if there exists this thing beta such that alpha is, the elements of alpha are the elements of beta scaled up by our D, not B. We then write, in this case, that beta is alpha over D, which we see is obviously going to be unique if this exists. And that motivates the following lemma, which is that let n be an integer greater than 0, a positive integer. Take n indeterminates and n elements. N, I guess these are just all going to be integers. Let C alpha for alpha being a list of n copies of n, and non-zero be a family of elements of the integers such that 1 minus the sum from 1 to n of ui ti is the product over non-zero alphas. 1 minus t alpha to t minus t to the alpha of C alpha. Then for all alpha in being an n string of n natural numbers and not 0 as a whole, we get that C of alpha, going to let C of alpha, we see that C of alpha, this is our lemma, is that C of alpha is 1 over alpha times the sum of D dividing alpha of the Mobius function of D times the absolute value of A over D factorial over alpha over D factorial times U to the alpha over D. The proof. Our first formula, which is the 1 minus sum of UITI, is equivalent to, we just take the natural log on both sides, so log of 1 minus I equals 1 to n. There's not really any reductions to do here. And on the right side, this product is going to turn into a sum across alpha being non-zero This is also going to bring down this exponent to be a multiplicand. C of alpha times log of 1 minus t alpha. So that we get, if we take the negative on both sides, we get that 1 minus log of 1 minus the sum of uiti is equal to the sum for j being at least 1 of 1 over j times the sum for I from 1 to n of uiti to the power of j, which is equal to, for the sum of j at least 1 over j times the sum for size of beta being j, factorial of beta the factorial of the absolute value of beta over the factorial of beta times u to the beta times t to the beta, which is the sum for the size of beta positive of 1 over factorial of beta, factorial of beta, factorial of the absolute value of beta over factorial of beta times our u beta t beta, just some good old symbol manipulation. And we also have that negative of the sum for non-zero alpha, this is our right side of the above, of c alpha log 1 minus t alpha is the sum for absolute value being positive, of alpha being positive, and k being at least 1, of 1 over k c of alpha times t to the k alpha, which is the sum for beta being positive and k dividing beta of 1 over k times c of beta over k times t to the beta. So we get the sum across k dividing beta. We can equate these two to get that of the absolute value of beta over k times c of beta over k is equal to the factorial of beta of the absolute value of beta over the factorial of beta times u to the beta for all beta being a string of n natural numbers, non-zero. Now let capital lambda be the set of elements lambda I in as strings of n naturals, not all zero, such that the greatest common denominator, the GCD of our lambda i's, is 1. Every element of the natural n to the n minus 0 can then be written uniquely as m lambda, where little lambda is in big lambda, and m, of course, is going to be the GCD of all the components. Thus, we get this equation in the form of the sum across k dividing m of m lambda over k times c of m lambda over k being equal to m times the absolute value of lambda factorial over the factorial of just m times lambda times u to the power of m lambda. So by the Mobius inversion formula, we get that this above equation is equivalent to saying that the absolute value of m times lambda times c of m times lambda is equal to the sum for d dividing m times mu of d times m lambda over d size factorial over m lambda over d not factorial, not absolute valued, factorialized, times u to the m lambda over d for all lambda and lambda, m being at least 1. Next theorem. Let X be a finite set with a cardinality of n. Part A is for every integer at least 1, LR of X is free of rank CR be equal to 1 over R times the sum of D dividing R of Mobius D times n to the R over D. And B giving for all alpha in our natural numbers indexed by x and non-zero, our alpha x, the multifiltration alpha of x is free of rank C alpha, which is equal to 1 over alpha times the sum across D dividing alpha of Mobius of D times the absolute value of alpha over D factorial over alpha over D factorial. And the proof of this we know that LR in X and L alpha of X are free. We've already shown that. Consider the multi-graduation A alpha of X for alpha in NX of AX defined by the canonical homomorphism phi of the free module of X into the integers indexed by X and then A alpha of X intersection of Lx is our L alpha of X. For alpha in R and X, the K module of the free algebra, the alpha grade of the free algebra of X, admits as basis the set of words in which X occurs as a letter alpha X times. Let d alpha is going to essentially count these words, so it can be the rank of I'm assuming that's supposed to be alpha of X. We shall calculate the formal power series P of Tx for X in X inside of the formal power series on the integers on our Tx, X in X, defined by the power series of our T being the sum across alpha in Nx of d of alpha times t to the alpha. We have then that P of t is the sum across M in the free module of X, T phi M is equal to the sum across R from 0 to infinity times the sum of all xi across all sequences for x1 through xr, the product of the txi, which is equal to the sum from r equals 0 to infinity of the sum across x and x in tx to the r P of t is 1 minus the sum of x in x tx to the minus 1. Hang on, there's some weird notation going on here. Alright, anyways. Then, for all alpha in nx minus 0, let E alpha j from 1 to j to c of alpha be a basis of L alpha of x and give the set I of ordered pairs alpha j such that alpha is in nx minus 0 and j is between 1 of c alpha. This is our I, and we're going to give it a total ordering by Poincaré-Birkhoff-Witt. The elements of the form y sub m being the product along alpha comma j in I of e sub alpha comma j of m alpha comma j, where the index m runs through our natural numbers indexed by I, forms a basis of free algebra of X. Each y sub m is of the multi-degree of the sum across our pairs alpha j in I of m alpha j times alpha, which we are going to write as u of m. Then p of t, parses of t is a sum across m in ni of t to the u of m, it's the multi-degree of m, which is equal to the sum across m in the naturals to the I times the product of alpha comma j in I times t to the m alpha comma j times alpha, which we can swap these around to get the product of alpha comma j in I times the sum of r equals 0 to infinity of t r alpha, which is the product across alpha j in I of 1 minus t to the alpha to the inverse. So we get the notation in this book is getting really badly formatted as it goes on. P of t, I'm guessing this has to be equals, which they did not write, alpha in n to the x minus 0 of r1 minus t to the alpha to the minus c alpha. So by comparing this with our previous result, we get that 1 minus the sum across x and x of tx is equal to the product of alpha being in nx minus 0 of 1 minus t alpha to the c alpha, which gives our b. And so this gives b. If we substitute an indeterminate u for each tx, we get 1 minus this tx is going to be n copies of u. It's going to equal the sum across alpha in n x minus 0 of 1 minus u to the size of alpha to the c alpha, which is the product for positive r of 1 minus u to the r to the c of r, which gives a. And we can actually calculate some of these values explicitly. So for example, C of 1 is n. C of 2 is 1/2 of n squared minus n. C of 3 is 1/3 of n cubed minus n. C to the 4 is 1/4 of n to the 4 minus n squared. C to the 5 is 1/5 times n to the 5 minus n. And C to the 6 is going to be on its own page. C to the 6 is going to be 1/6 times n to the 6 minus n cubed minus n squared plus n. And this comes with a remark. Let X be a set, and let alpha be in copies of naturals indexed by X. The rank of the free key module L alpha X is given by a formula up above. I will find it again, point out exactly, make it unambiguous. It was just our hypothesis B, which was, I'll probably need to go like this, which was, we saw this B formula here at the top gives our rank of our free Lie algebra as a K module. And we get this from our previous results. It's been less than half an hour. We're gonna start our next chapter, but it's kind of always awkward to do it mid-video, but that's how it goes. So we're looking at now, our next chapter here is central filtrations, specifically real filtrations. I did not get a chance to look through this, so I'm hoping this is pretty distinct from what we saw before, but given that we've already been working with filtered and graded sets, graded algebras, I'm assuming they've already covered here everything up to like what we've seen already before in SARE. So let's find that out. Alright, so start with the definition. Let G be a group. A real filtration on G is a family of subgroups of G such that G alpha is the union of G beta for beta less than alpha for all alpha in R. This gives that G alpha is going to be inside G beta for beta less than alpha, so our family G alpha is decreasing. Our filtration is said to be separated if the intersection of all G alpha is the identity, and is an exhaustive. Alternatively, if G is in the union of all G alphas. Remark: let G to the n over n in our integers be a decreasing sequence of subgroups of G. For every integer n, I always keep writing n for the integers, I don't know why. And alpha in the interval of n minus 1 n, we write that h of alpha is in G of n, so essentially h of alpha is equal to G of n, so essentially, so written better, h of x is G of the ceiling of x. Thus we get an integral filtration, if you remember from Serre. This is, of course, a real filtration. A being algebra, a real filtration, a real filtration, a sub alpha on the additive group of A is called compatible with the algebra structure if A alpha times A beta lies within A alpha plus beta for alpha and beta in R, and likewise K on alpha, A alpha is within A alpha if the filtration is exhaustive. A alpha is a fundamental system of neighborhoods of 0 under the topology of A, which is the one compatible with its algebraic structure. Let B be a unital algebra. A real filtration B alpha on the additive group of B is called compatible with the unital algebra structure if it is compatible, it is compatible with the algebra structure, and 1 is in B0. Okay, my phone's glitching out. That's pretty cool. Now let's look at the order function. Let E be the identity of our group G, and our G alpha a real filtration. Let's rewrite that actually. For all x in G, let Ix be the set of real numbers of alpha such that x lies within G of alpha. If alpha is within I of x and beta is less than alpha, then beta is an I of x, so I of x is an interval. Also, I just noticed I wrote of here, which just makes sense. Real numbers alpha, so that x is in the alpha filtration of G. We also see that Ix contains its least upper bound when it's finite. Thus, Ix is of the form the open interval of negative alpha, of course, with to the closed side with a Vx intersecting the reals. That's the ray from V of x down. With V of x being in R bar. So V of x is the supremum of alpha for x in G alpha. The mapping from above of V of our group G into the extended real numbers is called the order function. I don't even know what I wrote there. Order function associated with the real filtration G alpha. And V of x is the order of x. Then we get the following properties. Alpha for x in G and alpha being a real number. X is in G alpha if and only if the order of x is at least alpha. B for x and y in G. We've seen this before. V of the inverse of x is v of x. V of the identity is positive infinity. V of x and y is at least the infimum of v of x and v of y. And these are equal if v of x is greater than v of y. Not sure what that, I'll have to look into that. For all alpha in the reals, let G plus alpha be the set of x and G. Let G alpha be the set of x and G such that v of x is at least alpha. Then G alpha positive is the union of all beta at least alpha of G beta is and this is a subgroup of G. Now we've seen this before, that VB mapping of G into R, satisfying B, for all alpha in R, let G and alpha be the set of x in G such that V of x is at least alpha. And then G alpha for alpha in R is a real filtration of G with order, one second. With order function V. Filtration G alpha is integral if and only f V maps G, the order function maps G into Z with of course positive and negative infinity. It is exhaustive if and only if nothing gets sent to negative infinity, and it is separated if and only if only the identity gets sent to E, set to positive infinity. Now, let A be an algebra. Sorry, I had to read what exactly I'm going to be doing here. By the above, the relation of x is an A of alpha, A sub alpha if and only if v of x is at least alpha, defines a bijection of exhaustive real filtrations A alpha compatible with the algebra structure onto the set of mappings of V from alpha into the extended reals not taking on the value of minus infinity and satisfying first off Vx plus y is at least the infimum of Vx and Vy. V of minus x is at least is equal to V of x. V of lambda x is at least V of x. V of x plus y, V of x times y is at least V of x plus V of y. And V of 1 is at least 0. We also know that if V of x is not everywhere positive infinity, we get that V of 1 is equal to 0. And with that, we have actually finally covered a full video length. I know yesterday I went under a lot, so today I'm kind of like starting to put in measures to make sure sometimes like change my standards on the videos length so that I actually get like a full study session in with each video. And I do think, well, some of this lines up with what we've seen before. It's on the fact that it's on a group structure and the fact that we're going into more depth, I think means it's alright to cover as a video, even if it's a bit familiar, hopefully. I don't know. Thanks for watching.